So in the last class, we finished the proof of NL equal to co-NL, right? So recall that NL is essentially the question of graph reachability in directed graphs, right? And co-NL is the directed graph unreachability problem. And we showed, which was a surprising result, that these two classes are the same. So unreachability can be converted into reachability. The way we did this is we used non-determinism to count the number of paths. Okay, so these yellow points, these are the important points which helped us in actually just enumerating all the paths to distance I. So once we have shown this, we actually can say something about n space and co-n space as well. So what we can say now is that for all functions at least log n, right? So NL and above, all these classes, n space S, there also the same proof works. Okay, so n space S is co-n space S as long as S is at least log n, the log n function. So how do you show this? So you do the same thing as was done above. So let M be Sn space NDTM. Deciding a problem or a language L. Now you know that the configuration graph G of Mx okay, this is Sn space computable. As Sn is log n. So that x can be indexed. Right. So every entry of x, just to locate an entry, a location, you will need log n bits. But once you have this much of space, then you can essentially compute in big O of Sn whatever you want in the configuration graph. Here also I can put big O to be safe. Okay, so the configuration graph is computable in Sn space. And computable means, I mean, you don't want to output the whole configuration graph, but just any vertex and its neighbors. Okay, so locally that information can be computed in Sn space. And so this means that x is not in L if and only if G, the start configuration and the accept configuration is not in path. Right. So in the graph, x not being L converts to this unreachability problem, and this unreachability problem you do exactly what we did in the previous proof. So now invoke the previous proof method to deduce that L complement is in n space. Okay, so L complement reduces to unreachability or path bar you can reduce to path, as we did in the previous proof, NL equal to QNL proof, which means that n space S is co-n space S. Take containment both ways. Okay, so that finishes, so that means we don't need to worry about co-classes of non-deterministic space. Right, and remember that n space is contained in space S square. So that also we can make a note that co-n space S is contained in space S square if S is greater than log n. Okay, so up to a mild blow up, n space, co-n space, they are all actually in space. Okay, this is an amazing thing about space, which is not known to be true about time. Okay, so this topic is done. Now what we will begin is a new way to define complexity classes by oracles. So now next we build classes using oracles. So the topic is called polynomial hierarchy. So the motivation is in computability theory. This has been done before. We can create a hierarchy of problems by using the halting problem. So basically, what are the problems that you can solve using the halting problem? Yeah, if you ask that question, then you will get problems that are even harder than halting problem. So consider Hall Turing machine as an oracle. And consider problems which can be solved using Turing machines with halt as in given as an oracle. Okay, so whenever halt instance is to be solved, it will be written on the oracle tape, and immediately halt will solve it. Okay, in one step, it will immediately go to this these new states Q yes or Q no. So halt can be queried. So now what can you solve by such Turing machines? And once you have this, then you can go to the next level, which is Turing machine halt. So let me instead write it like this. The set of problems here is C, then H to the halt, and so on. Okay. So Turing machine with halt as an oracle, the problems which you can solve like this, in it give, okay, let me instead write like this, Turing machine with H. Okay, so next is this is H2. Okay, so Turing machine halt, then Turing machine with halt as an oracle, then those problems given as an oracle to Turing machine, a new class H2 appears, and so on. So these are the new classes, right? And you can show by diagonalization argument that they are all becoming harder. So these are provably getting harder. So so halt will be easier than H1, H1 will be easier than H2, and so on. This you can show by diagonalization argument as an exercise. So now the question is, what is the complexity analog of this? Okay, so similar thing can we also take a supposedly hard problem like SAT, and then build a problem that is harder than SAT, and then use that problem to build a problem harder than that, and so on. So this infinite hierarchy, can we build an infinite hierarchy, and will we be able to give a proof that it's actually a hierarchy, strict hierarchy? Okay, so towards that we will show, or we will define the polynomial hierarchy. So PH will be a generalization of NP. NP and co-NP, and it will lie well below P space. Okay, so in other words, we will attempt to create a hierarchy of harder problems, increasingly harder complexity classes while remaining within P space. Okay, such a thing you had seen also inside PNP via Lardner's theorem. Now we will go actually outside NP, end up in P space. Okay, in fact below P space. So to motivate that, we'll actually define it in two ways. Today we'll define it via quantifiers. Next time we'll define it via oracles. So let us motivate by a problem. So consider the following optimization question. Which I mentioned in the overview of this course. It's called min DNF. So what is min DNF? It's those formula instances that are already optimal. They cannot be made smaller. So phi is DNF formula not equivalent to any smaller DNF. Okay, so if you look at its size, it cannot be further reduced. If you reduce it, then it will not be equivalent. If you look at psi smaller than phi, then psi and phi will not be equal. So another way to define this, so alternatively, min DNF is, it is the collection of those formulas such that for all DNF psi, size of psi less than size of phi means that there exists an S satisfying assignment such that psi S is not equal to phi S. Okay, so for every DNF psi that is smaller, there is a distinguishing assignment. Okay, so that's what min DNF is, collection of minimum DNFs. And if you think about this, this seems to be harder than SAT. Okay, it's an interesting optimization problem, but it looks harder than SAT. Why is that? Because it has two quantifiers. There is a for all and then there is a there exist. Let me not use implication here. For all DNF psi with psi less than phi, there exists an S. Okay, so after for all there is a there exists. Double quantification. So it seems beyond NP, which is kind of defined by there exist quantification, and co-NP, which is defined via for all quantification, right, negation of there exist. As min DNF uses both for all there exist quantifiers. Right, so since it uses both, it's like co-NP stacked over NP. Okay, it's this is exactly the place where you should, it should remind you of oracles. Okay, so then it intuitively min DNF should be harder than anything in NP or co-NP. On the other hand, if you want to give a brute force algorithm, what you will do is you will go over all the psis, right, and check whether phi and psi are equal or not, whether there exists this distinguishing assignment S or not. That you can implement in P space. So on the other hand, min DNF is in P space and doesn't look as hard as QBF, right? It doesn't look as hard as QBF, quantified Boolean formula, because in QBF all the variables were quantified. So there were n quantifiers alternating. Here there are only 2. So it doesn't look as hard as QBF. It is in P space and looks harder than SAT and tautology, SAT and taut, right? Somewhere in between. So this deserves a class of its own. So let us do that. So this motivates a class of its own, which is the subject of this lecture. So language L is put in pi 2. Okay, this is what we are defining. So pi is sub 2 and super p, right? Superscript is p, subscript is 2. So language L is in pi 2 if there exists a polytime Turing machine M and a constant C such that for all input strings x, x is in L if and only if for all, so we are quantifying this new string u with for all, right, of this blown up length x to the c. So for all large enough strings u or slightly bigger strings u, there is a certificate v. Okay, such that this sort of so think of v and u and v as extension of the certificate string that you used to have in NP, and think of M as a extension of verifier Turing machine. So the verifier x should accept M x u v equals 1. Okay, so x will be set. X will be a yes string if and only if for every string u there is a certificate. Okay, and the length and the time of M, everything should just be a polynomial blow up in the input size, which is size of x. So if I remove u, it's NP. If I remove v, it's co-NP. Okay, so let me maybe mention it so that it helps you to read. So this is kind of the co-NP part, and this is kind of the NP part, and we are mixing the two here, right? And now for all there exist, if I flip it to there exist for all, then I call it sigma 2. So language L is in sigma 2p if there exists a polytime Turing machine M and this constant c greater than 0 such that for all input x is a yes string if and only if there exists a u this size is as above. This again just some poly blow up of the input, and for all v mx uv should be 1. Okay, so you can think of this part as the verifier. In pi 2 it was co-NP kind of definition, then NP kind of definition, then a verifier. In sigma 2 it's the opposite. It's the NP kind of definition, then co-NP, and then the verifier part. Right. So for all there exists gives you pi 2, there exists for all gives you sigma 2. And you can show as a simple exercise that sigma 2 p is equal to co pi 2 p. Okay, so sigma 2 and pi 2 are just the co of each other, right? Because when you do negation, you can see that there exist flips to for all. So since negation of there exist is for all, and negation of for all is there exist. And yeah, so we can also define sigma 1p as NP and sigma 2p as co-NP. Sorry, sigma 1p and pi 1p. Okay, so the subscript denotes what level you are at. So first level will be NP co-NP, and the second level will be sigma 2 pi 2 as defined above. This is also the number of quantifiers, and the p here is just denoting polynomial time verifier. Okay, so I hope this definition is clear. Though it looks very long, it's just a truncation of QBF. Okay, QBF had n quantifiers. Here you just have 1 or 2, and yeah, you can all go down and define actually sigma 0 and pi 0 as just polynomial time. Okay, so these are the definitions at the low level. Okay. So let's quickly see some properties. So first is this min DNF problem. This now has its class, which is pi 2. Right, because if you look at the definition of min DNF language, it's for all there exist and then a simple test. Right, for all psi there exists S and then a simple verifier. So it is of that form, which is actually by design. So min DNF is in pi 2. If you look at the union of NP and co-NP, okay, both of them, I mean, NP is actually contained in sigma 2, and NP is also contained in pi 2. So is the intersection. Okay, note the intersection. So NP is in the intersection, and similarly co-NP is also in the intersection. So the union of NP co-NP is in the intersection of sigma 2 and pi 2. Okay, so sigma 2 pi 2 are really above NP co-NP. Okay, their intersection contains this. I mean, again, conjecturally, we don't know for sure. And where are these new classes sitting? What's an upper bound? So at this point, the best upper bound that we can think of is the same that we had for QBF, right? When you have lots of quantifiers, you can do an implementation in P space. There is an algorithm in P space. So similarly, sigma 2 pi 2 also sit in P space, right? So you can actually think of sigma 2 as there exists for all P, and pi 2 similarly you can think of as there exist for all there exist P. You can think of sigma 2 pi 2 as this, that it's the polynomial time class over which if you put for all quantification and there exists quantification, then you get sigma 2. If you do the opposite, then you get pi 2. Okay, just as a think of it as a shorthand for that long definition which we just saw. And once we have this, why stop at 2 quantifiers? Right, we can actually go on quantifying as we like and create these new complexity classes. So we can define, let me first write that. Define sigma I pi I by I many alternating quantifiers. Okay, so I equal to 1 quantifier, I equal to 2 quantifiers, I equal to 3 quantifiers, and so on. So a general definition would look quite complicated. It's here. So L is in sigma I if there exists a polytime Turing machine M and a constant C such that for all x is a yes string of the language if and only if there exists a u1, okay, and then for all u2 and a quantifier. This goes on alternating, and the ith quantifier is, let's say, qi. It's either there exists or for all, depends on the parity of I. If I is odd, it's there exists. If I is even, it's for all. M accepts. Okay, it ends, the quantification ends with the verifier test, which has to be polynomial time. So these are strings of length at most x to the c. Okay, so u1 to ui are these kind of certificate strings not too large, and this quantification, this kind of QBF, truncated QBF, should be true for yes string.